All right, that's going. Okay. So now we're going to get into how we do iterative reconstruction. In looking over this and having taught this now for several times, what I'm going to do is we're going to go through art, which I think is pretty simple today. And then next time we're going to turn art into BIP. And I think if you learn how to do that, turning it into SAP, and the rest will be okay. We're also going to want to do a couple other important things in here. So it's worth kind of noting. We're going to do a kind of quick recap of what it looks like. And then just a mention to you about, some ways we might be able to improve things. So we're going to want to leave lots of little tuning numbers. And I'm going to pick some reasonable numbers, but by no means the best ones, because the best ones that you can always tweak them and tune them and away you go. So we're going to write this so that you can do a lot of little knob turning. There are more things we could add than this, but we're going to try to go through the basic ones and explain basically what the knob means and how you turn it to try to improve stuff. And what we're going to do today is something that's going to be common with BIP, so you'll be able to use the same information then to extend to other ones. All right, so I just want to do, I know we did this just a little while ago, but I want this in your mind because this picture is the one that lets you understand how to write the code and how to add the tuning. So again, we're going to start with an initial guess, right? We're going to want that guess to be a vector. Right? Even though it's going to come from an image, we're going to have to vectorize the image. Okay? We take that vector, and then each of these green lines comes from one of the rows inside the A matrix. The A matrix is some projection history that's out there. Right? So we project it, right? And then we have some sequence where we're going to project it on a series of them, each one in turn. Right? And we noted that basically the further angles generally tended to give us, better tuning results, right? If small gaps really from x0 to x1 wasn't a very big change because they were really angle-wise close together. Whereas if you notice like from x2 to 3 or, from 3 to the 4, there were big changes because we had a larger angle. And if I had instead of gone from what we have 3 here to this one, if I'd gone from 3 to say like this one, that would potentially be a bigger jump. So, yeah. But we said doing too big of a jump can also be noise prone too, right? I want you to think about one other thing. If I had just kind of picked these in sequence, right? Here and then to the next one, it would have just gone here, right? And I would have kind of done this slow move around the outside. So it wouldn't have converged as fast. So this is one of those tuning things. What order do I pick them in? There's actually not a requirement, right? You're allowed to take them in whatever order you want. As we noted, some orderings might be better, right? And we know that idea about trying to get a little bit further. We talked about, somewhere, say high 30s to 40s is usually a pretty good idea. So trying to think of how might I be able to quickly reorder these. Because remember, we're going to have lots of them. So we're not necessarily going to want to spend a lot of time to do it, but we do want to make sure we make jumps that are fairly big. There is not a perfect agreed upon method for this. Okay? There are, in a lot of these areas, this is where you get from the science of engineering to the art of engineering. And make no mistake, engineering has art, right? Art as in the sense of, like in a science, you've got solid reasons and calculations and theories and proven evidence for it. When you get to art, you kind of have the experience and a gut feel. And this is when you kind of get to those. So I want you to particularly try some things and be wrong and fix them and change them or whatever, because that's the only way you're going to build the art part of our discipline. Okay, we feel good with this? All right. So, oh yeah, this is just showing the same thing, except doing the forgetting factor. So I put these in, right? Or sorry, the relaxation parameter. The red lines are, what if I had only gone, say, like 70% of the way, right? And that would build up, right? Because if I had went 70% of the first one, well, I could just start from there. But when I project down, I now have to project from that point, right? So you can kind of see that it moves around. But it ends up being on an inside track. All right, so we're going to start writing code. We're going to do like we did last time. What I've got here is kind of my outline of what we're going to want inside them. So you're welcome to type. I'm going to try to explain what I put on each one. So as you're typing them, they'll hopefully fit in memory. If you don't have MATLAB up, I encourage you to get MATLAB up. It's a lot better if you kind of try stuff and get feedback. It'll also show you errors and typos you might make. You know, I coded this all up in MATLAB myself just over the weekend for fun, and like every time I just like to write a new one. I'm not really sure why. Maybe I'm masochistic or something. But anyway, so I just wrote up over the weekend, and then you know, so I know it works. But then I cut and paste it, and the second it goes into PowerPoint butchers things like crazy. So there is a chance there is some PowerPoint butchering going on. But let's try to get what each one is, right? So we've got the basic function here. Function through end. Let me mention what the parameters are inside here. So angles that's up there, that's our 1 to 180. So just like you did with when you're doing filtered back projection. We're calling B, that's our sinogram. At the moment, I'm not even assuming you reordered it. We're actually going to reshape it inside here. So that's just, you know, I called it B instead of sinogram there. I was kind of torn on it, but B is the name we use because we do AX equals B for iterative, and sinogram is B. So I wanted you to be consciously thinking sinogram is B. Maybe a reordered into a vector version, but sinogram is B. X0 is your initial guess. So iterations is how many iterations do you want to do? Okay. Now, in general, for a lot of these, for the sizes we're doing, somewhere around 5 or 6 is probably right to get you a pretty good image. You know, when you get, well, it'll depend on your system. Depending on the system and how you pick your relaxation parameter and that, you know, it can be anywhere from the 10s to the 100s. I've seen a few systems that do thousands in cases. How big of a step are you doing? How comfortable? This is starting to get into some of the art of this for selecting how many iterations and how big of a step, right? We're going to be able to do fairly good size steps in here, so you know, we're not going to need as many iterations. Order is, again, an ordering of those, the reordering of the rows. This is going to be a vector, and it should have one entry for every row. So like imagine you had 10 rows just for simplicity. The normal ordering would just have these labeled as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But an alternate ordering might have 5, 7, 2, so on and so forth. Right, so what order, what sequence you put them in that, think of it like a list. It'll be a vector because it's MATLAB. But it's basically a list of what sequence do you want those to be in. Relax is the relaxation parameter. And then distance is going to be, when we're calculating the line, we're going to calculate the path that it followed along just in time. Right, so there's a lot of ways we could do this. We could pre-calculate the A matrix. There's all kinds of stuff. We're going to calculate each row when we need it. So when you calculate that, how far from where the actual line is to where the center is do you want to actually call it still part of that? All right. So if you imagine, I'll just put up a small, let's say like just a little 3 by 3 up here on the board for a sec. All right, and you can imagine I've got whatever a line goes through like this. Okay, the center of these we'll just kind of put these centers in here, right? You can imagine, clearly this one, we're going to want to call that one close enough. And clearly this one is probably close enough as well, as is that one. But how about here? So we've got a way to calculate these. And what we're going to want to say is how far these centers are off. If they're within some range distance, we're going to call them as part of the line. If they're farther than distance, they're not part of the line. So if you do kind of like the classic half, right, it's going to be pretty tight. I want to go less than that. As a matter of fact, particularly on the diagonal angles, you're probably going to want to do at least 1 over root 2. Right? Otherwise, you're going to have things that nick it. But how far? Right? Do you want to go a little bit farther? Do you want a little bit narrower? What you'll notice, if you pick it too small, you'll get these dark rings because they won't fully fill in, right? Because they're not wide enough. And so you'll get this kind of bright area, dark area. So if you get these kind of light and dark rings on it, you pick distance too small. That's generally what that means. So you can get them. Now, truly speaking, we probably should make distance a parameter of the angle that it's currently at. Because if it's coming straight in, half is probably better. Right? As you're going more towards the diagonal, I wouldn't want to go less than root 2. Right? So there's actually some variation between these. But, anyway, there's a lot more tweaks you could do, I guess is my point on this. But right now, we're just going to keep our life easy, we're just going to put this. Plus, we're writing this in script code. MATLAB script code runs much slower than MATLAB executables. So we're going to write it this way. It will be survivable for a 200 by 200 doing a recon here. If we were to put too many features in on our scripting thing, it would just run too slow. Right? So you'd have to compile them to get decent performance. We'll still be borderline. We'll make these machines heat up pretty nicely to run our versions, but it'll still be somewhat decent. Not as good as compiled, obviously, but it'll be okay. Okay, so everybody feel like they understand the parameters? Okay.
I have a question, sorry. For the distance parameter that you mentioned, you mentioned that we probably want to parameterize it by angle. So is that going to be a vector, or are we going to do?
Or that's something we would want to do if we're doing nicer professional code. We're just going to do a single number.
Okay, great.
And again, that's just for simplicity.
Yeah.
And again, a lot of this, like this is one that I really kind of struggled over. But what I noticed is the amount that I'm going to have you do here that's tuned in on my laptop, it would finish in the minute-ish range and would only make it overheat a little bit. It was blowing some pretty hot air. If I had too much in, I've done in the past, added a bunch more in, and I've had it take like 5-10 minutes to do them. Like really pretty cool stuff comes out, but it's like 5-10 minutes of my machine going. So yeah. Anyway, again, it would be much better if we could write compiled code, but that would require you to write a lot of back-end stuff, and I don't want to deal with that. Okay. So the first line there, that's just a knee-jerk reaction. Right? You should. I didn't put justification for that because you need to know how big your sinogram is, right? It just lets you know your detectors and your angles. And that's, I called them sino there, again, just to remind us that B is sinogram, somewhere near to the top. Then each comment is basically something for you to, I deleted one of the ifs I wasn't supposed to. Anyway, we'll get to that in a second. So we're going to do this in a series of steps. First off, we've got to kind of calculate the size of A. How big is A going to be? It means we need to know the rows and the columns. We want to find where's the center of the image, right? Just because it's referring, we use it later on, right? Medical imaging always lines up the center of the image to the center of the detectors. So knowing where the center of the image and where the center of the detectors is just kind of foundational. We're going to allow an offset between those two centers, because remember we said if you line them up too perfectly, it also tends to enhance those rings. So the offset will let us break the rings up a little bit. So that's a nice added feature on there. So we'll do that after that first comment. Second one, right, we want to take, so we're going to have an initial image estimate, that x0 that's passed to us, and we're going to have figured out from all of this, from the A and everything, we're going to figure out the size of the actual image. Well, what if the size of our actual image does not correspond to the columns of A? Right, they're calculated from different areas. What that tells you is they sent us the wrong sinogram, or they sent us the wrong initial estimate, because either way, right, there is an implied from that sinogram, there is an implied size of an image we're going to try to reconstruct. And from the x0, there is an implied size of the image we're going to reconstruct. So if they're not the same, what went wrong? Did they give one too big, one too small? How do we adjust it? We don't know, right? So we're only going to do it if that. Now there would be a whole bunch of other things we'd probably check in real life, but that's a dead minimums, right? If they don't send us the right size data, then it's wrong. So there should be an if statement at that point. The setup grid for calculating the matrix. Remember, we have to do the just-in-time calculation of AI. Remember, we have to make a grid, and then we're going to figure out which one of them go in. It's helpful in MATLAB to use mesh grid. So we're going to set up a grid before we do the iteration count, so we don't end up doing that inside the loop. So that's just a reminder, set up your mesh grid before you get in. Then we're going to do our iterations. So I just have the 4, and we'll run through one for each iteration. And then inside the iterations, we've got to run through all of the rows of A. So we have a double nested for loop. How many iterations do you want? How many rows do you have to do? Walk through one projection per row. Away you go. And then once we're on that very inner part, we're going to have to reorder the histories according to the ordering. We'll calculate our AI just in time, right? And then now that we know AI, we'll apply the projection because we know AI, update the estimate, and move on over. And then, of course, there's a cleanup stage, which says it's after we've done all the iterations. We'll have a calculated matrix, but it won't be counted as an image matrix. The scale could be off and things like that. So we're going to want to turn it back into an image before we send it back. All right. So notice, the steps I described here were perfectly understandable from those pictures. All right? And this is kind of what I want you to think about. Before you go in, everybody's first reaction, start writing code whatever you want. All right? But I want you to kind of think of this. I've got my setup areas, I've got my do it areas, I got my cleanup areas. If you follow this type of procedure, and I've got my notes, what do I have to do with each one? It'll keep us on track, and it'll help us to do this in a reasonable way. Good? Awesome. Now, this is going to grow kind of ugly, so on the next slide, I'm going to jump over the bottom part of this to the other column, because this is backwards compatible. I actually started the code at the very end, and it took 1.5 columns to fit, and then I start hacking things out. So it's a pre-affirm of where it needs to happen, but I put them together on this one just so you can see them cleanly lined up. All right, so we're going to start with the very first part. All right, what we want to do in this very first part is calculate the size of A and all those. I left in the first lines what we have to do for each one of them, just because I figured that way we keep our names consistent. But like for instance, given that I know the sinogram size, how would I figure out how many rows in A? Right? Anybody got an idea?
Are we assuming that A is, each row of A is an image in one long vector?
Yeah, so A is a matrix, each row is the path that particular X-ray in this case So through the object. Right.
So the number of rows should be the number of angles.
So the number of rows should be equal to, there should be one per, it's more than just angles, right? Because think how many, for each angle, how many actual measurements do you take?
Oh, I see.
Yeah, right, so each row tells you one detector's measurement at an angle. Does that make sense? So there should be as many rows of A as minimums as there are, spaces inside of your sinogram. So that's figuring it that terms, right? Because you're going to reorder the sinogram into a single vector, and there has to be as many, however many items in that vector has to be equal to the rows of A. So that's your first one. You are welcome to put your guess on how to do that, right? So how about N, right? That's the image size. How do we know how big the image was?
Are we wanting it to be even with the last time? Or matter?
We don't have to force this one to be even.
Okay. Just,
But we will want a square image.
okay. Fair enough.
In general, we often assume square images. Right? And part of the reason is if you don't assume square images, then somebody's got to give you extra information. Aspect ratio or something. So we'll assume square. Do you remember how we calculated?
Could you just square the size of X file?
Ah,
Divide by the number of,
so that would be one way of doing it, right? Because they give me, if I take a look at how big X naught is, we're going to want to get two ways to guess how big X should be. Because that's the check we know we have to do. That's why I included that one there, right? So I have to see, was the initial image the same as what we would guess from the sinodetector's size or the whole sinogram size. So if we look at the sinogram, how would you know just from the sinogram how big the image should be? Right? Close. Think about those detectors. The detectors have to give you a big enough image to hold the whole thing, right? They're rotating around. Right? Assume each detector is size 1, right? 1 square big. So how big, what's the worst case scenario for my detectors trying to read an image? What's that?
45 degrees.
So you want it, yeah, the 45-degree angle ones, which means, how's it going to relate?
Divide by root 2.
Yeah, the root 2. Right? So just that one is going to be related by root 2 to the original, right? Because you want to count the diagonals. Okay. Remember, n over 2 is literally just, that's my shorthand for the midpoint, which is literally n over 2. Division on some machines is really slow, so I usually don't like to count that it's there. Some embedded processors don't even include division. So you sometimes have to get at other domains. So if this is being done by an embedded processor, you may or may not have division available to you. So a pre-calculation of it can be helpful. How about the columns of A? How many columns should A have?
Same.
Same as what? Rows of A?
Should be n squared.
So why n squared?
When you flatten out your image into one big row, you gotta have one piece of information for each pixel.
Yeah. Right. Each of the columns corresponds to a pixel or a voxel. We usually do 3D. You have to have one for each, so you have to give, there has to be spots for them. Right. How about D2? What do you think D2 is?
the physical distance from the center of the detectors to the
Yeah,
edge?
it's the center of the detectors, right? That's just following, we did that same thing, right? D in our previous one had been number of detectors. In this case, I kind of wrote it out longer, cyno detectors, but it's the halfway point for them. So what's that if-else construction doing? What's the if statement asking? Let's give it a shot, right? Everybody's being quiet, or at least last one, right? It's better to take a guess and be wrong in a meeting than say nothing. I'll be real honest with you. When you're out working in industry, right? Somebody who's taken reasonable guesses and willing to speak into the group, people just remember them as active.
So
Yeah.
D2 is our is the center. This is the center of
The detectors.
That's that. And then the cyno detectors is our cynogram.
It's a count of what?
It's a count of one.
It's a count of what?
Of what?
Number of detectors. So what would cyno detectors minus 2 times D2? What's 2 times D2?
The whole day.
So that should get me back, right?
Yeah.
And obviously D2 is related to cyno detectors, right? So they should be the same way. Even. So think carefully about, right, when you do this, we want D2 to be an integer. What if it was 5? Right? Well, when you divide by 2, it's no, D2's not an integer then. Right? So obviously we're not too thrilled on that one, right? So we're going to have to get rid of that fraction. And then when we multiply by 2, you're multiplying by 2 something that dropped a fractional part. So what is cyno detectors minus 2 times D2?
Tells you how many halves you have left over.
Which, what does that mean as a number? When is that number going to be bigger than 0? I agree with you, it's the number of.
If you had to truncate. If it was odd number of detectors.
Okay, so if it's bigger than 1 and I have to truncate, what type of number is that? It's odd. So this is an odd even detector. How many detectors are it? Is it odd or even? Which one's odd? The if or the else? The if is odd, the else is even. So that's what we're saying, what do we want to do for those offsets? All right, so pick what you want. Now, I'll give you my guess for what they should be. But whatever you pick, live with it till the end, because I want you to try it and see what happens with different choices by doing that offset. Offset is a parameter you can choose, right? So by selecting different offsets at these points, it will have some effects on it, and I want you to see what it looks like. Because sometimes people get these things wrong. And how do you know when it's something wrong? You just have to have seen it blow up and go, oh, I remember what that is. Okay. How about size of x0?
So we can make sure that the x naught fixes or matches the b we were given.
Yeah. So that's just, we're just going to pre-calculate it. Right. It just saves it and makes it a little bit cleaner. Right. And then we're going to want to do check to see if the initial image is the same size. Right. And I should have done that x0 or x equals is not actually correct in that. That was actually from the previous line. No, I deleted it and carried up and I didn't notice it. So that is not even correct for that. So don't have x equals right? There should be no semicolon. I didn't notice that it carried up weird like that. Okay, do we all have guesses? We kind of walked through it when we were doing it. Does everybody have what they think their code is for them? Sure. All right, the best guess on, or the best thing to do actually for your learning in any of these situations is try to make a guess. So when you're trying to learn code, try to figure out what needs to happen for each one, write your own statement and then check it. Even when they give you code, don't immediately just read their code. Because if you read somebody's code in a new language or it's a new algorithm, if you just read the code, what you're gonna do is go, oh, that makes sense, right? Because it will make sense. But your brain only stores new information in it. If you look at it and you're like, that doesn't make sense. Because if it made sense, clearly what you knew was sufficient. So your brain goes, don't worry about it. So if you've ever wondered why you've read stuff and then 15, 20 minutes later, you're like, what the heck was that? It's because your brain said unimportant and it never released the learning chemicals. So that's why I want you to try the ideas even if you're wrong. Because being wrong doesn't cause a problem. You're going to get the correct answer in a second. We'll explain it. And then your brain will go, oh, I didn't know that. Frustrating. You'll release the learning chemicals. And then when you get the right answer, you will learn it and you'll remember it forever. And if you were right, you'll be like, yes, right? But it'll still cause it to underscore in your head. So either way, it's a good spot. We ready? Okay. So we had mentioned the rows of A, it should be one for every element inside the sinogram. So I just take the two sizes and multiply. Right, that should give you the full size of it because it's a rectangular grid. And I made mine even. You don't have to, so I said you don't have to make yours even if you don't want to. And technically speaking, on the next thing, when you're coming in, probably a good idea not to, but anyway, I did it because I have a habit of making things even inside them. But if you want to write the sinodetectors divided by square root of 2, with the floor is perfectly fine. Yeah.
Why did you subtract 2 off the end of your end line?
So it actually, there's always a bit of blank zone around there, and this estimate, most people usually actually make their image a little bit smaller. They typically have a dead zone on the end of it. So if you look at the way MATLAB does theirs, if you want yours to correspond to the same size as MATLAB, there's one dead pixel on either side.
Okay.
At the maximum extent. So that's what MATLAB does. Most systems will have at least a certain amount of unneeded ones, because what you'll get is you should get full energy photons or protons or whatever coming in. There should be no disadvantage. So that's just a way to check to make sure the thing was really centered and somebody didn't stick an oversized object inside there. So it's a good way to kind of verify that you're not partway through. So yeah, if you look at yours and you don't put the -2 at the end, you'll notice, wow, I did a 128 size phantom, when I created the phantom, but I got an image size 130. And if you remember, that's what we had before. And that's because of those dead pixels on either side. They're not really dead, they're, making sure you're centered. Good question, right? The N2 is, of course, there. If I hadn't made it even, then I'd have to floor it. But no worries. How about the columns, right? You should have gone the n squared, right? Because it's a square image. So I had for D2, it's sinodetectors divided by 2, floored. And again, that's our round down. And then I did, and this might seem odd to you, for the odd ones, I subtracted a half. And for the even ones, I subtracted 1. Did anybody get something different? I'll explain my why, but if anybody got something different, it's not bad if you have something different.
I flipped it too.
Okay.
Yeah.
So let me ask you, why put them in that way?
I mean, a little bit was I was just kind of guessing.
Yeah.
But, yeah.
Oh, totally cool. All right. And it's fair to say that you're guessing, and it seems reasonable, right? It's kind of already odd and everything else. The reason why I guess this one, and this is not, if I was reading it, about 0.75 is usually actually a little bit better. But in any case, you could try a different one. The reason why I did the 0.5 on the odd is because the odd already has the floor in it. So it's probably already lost a half already. So that's really technically, this is going to make both of them about the equivalent of -1. That makes sense? So, you know, that's why I picked those the way that I picked them. But keep it and try it, right? You know, and you'll see, you'll probably get a little bit stronger of a circle than I will forming up. But it's worth taking a look at. Anybody pick anything different?
What's that happen? 0?
For which one you had 0?
0 for the even and then plus a half.
So what was the odd?
Odd was plus a half. 0.
So it's basically the same thing, it's just you're on the other side. You know, I would imagine that's probably going to be fairly reasonable. You'll probably get a little more wobble side to side. You know, just because you're getting further away. Generally, we tend to pull it towards the negative end because that's closer to where they actually set it. Usually when you're doing them, you ideally want to set it so it's a partial pixel off, and usually towards that negative, the lower end when they first estimate. So if you go further the other direction, it probably won't show up in that as strongly. But on a real physical system, they probably already have a slightly skew that direction. So you might be further away, and so you might get a little bit of a fuzzy edge off. But you know, again, probably still a decent zero. So those are good things. In each case, right, just think about what it is and then try to see how does that affect it. Because what you're trying to do is calibrate in your mind, how does that work and what's the net effect look like. Okay, the size there, that's really just because I don't like writing the length. You can see I just check, were the columns of A the same as the size of 0? I could have technically put that down here. I guess it's not that much different. I just always pre-calculate stuff as I have it. And then I set this is for later on. We're gonna keep using X as kind of what we're working on. So I just have this habit of, you know, when the X0 comes in, you just say, okay, this is my current X that's coming in. Okay, so far so good? All right, so that's our setup. Let's kind of jump into the next one that's in, right? So that actually got most of the things here. I'm gonna reserve this one for the setup lines and that for when we get to doing that, which is kind of on the applying the projections and all that stuff. So following that same thing, that is really, this line here is really for those, so I leave it to later. So just ignore that one. So now we're just kind of filling in, this is just that kind of junk walking through, right? I made this X, so I'm just saying, you know, X is equal to net X next. At the end of each iteration, we generated X. You can see it over there at the end, right? Because that's what we're gonna wanna take as the image output. You don't wanna claim X next, because what if it was partway through or whatever, right? It's just nice to know, okay, I sampled X next here, as opposed to I got partway through and hit a break or something, right? So I like to say, okay, I know at the end of that, whatever next I had generated is my image I want to take out. And so this one says, if I'm doing more than one image, I should take that good image from the last one. X next is the one I'm gonna be working on, right? That's my current best estimate. When I'm walking through for each one of these, right? The X next I end up with, I'm gonna, at the start of each one, what was the new estimate becomes the old estimate, right? So what was the new estimate becomes the old, and I'm gonna have to figure out a new one. So that's why you know, it looks like I keep redefining stuff by different ones, but you need to inside the for loops. So you make sure you're grabbing the correct estimate and not just grabbing something partway updated. So this just makes it very clear, right? At the end of this for loop, I want X. So what's going to come in will be X. And I probably should highlight that one here just to show that connection. Right? When I'm doing the individual things, right? My previous estimate was X last, and I'm generating a new X next. So I've got to take the previous projection, it becomes the old one, calculate a new one. The new one becomes an old one, calculate the next one, right? So on and so forth. So I have to be able to reuse these names, and that's all these do is make sure I'm putting the correct value into them. Does it make sense? This one I didn't give you stuff to do. This is pretty obvious. All right. So remember, order was a vector. Why that?
So you don't just go from row to order. Well, you can define the order. That's like,
The order is definitely right, but I could just, why not order I? That would, in most languages, that would make sense, right?
that doesn't like zero.
Yeah, darn them, right? Because they do that stupid count for one thing. But most loops make much more sense from 0. Right? When you're actually calculating stuff, 0 is the right number to start with. You know, it's that same ridiculous thing that goes on that there's no AD0. So calculating years is always kind of ridiculous. Okay. So that's just a note. That's just taking them. Why is order, you know, the I plus 1 is obviously just my for loop number. Why is this row? How does this reshuffle and reorder stuff?
Well, if you didn't pull it from the order vector, it would just go in order sequentially, but now you can, whatever numbers are in your order.
Yeah. So I is really what would be the normal ordering I would take it. This order vector is a permutation. Right? So it's just giving me a reordering of those. So all I have to do is literally stick it into there. You could also calculate that one just in time too, but I did it this way because I thought it would be easier for you to visualize. Okay, now we just want to think. We're going to have to do some calculations. This is just a reminder, right? We're going to take these. You've got, this is what your image looks like, and we need to vectorize it. Right? So this is going to be your AI in particular, right? This is a row in A. Okay? And therefore, this is how it's originally set up, right? Something goes through there. This is actually an image itself of X, but same idea for the other ones, right? We're going to take them and we're going to do row-wise slices, not column-wise. Why row-wise?
To be consistent with linear indexing?
Yeah, because of MATLAB. When you use MATLAB's built-in commands, that's the way MATLAB chops it up. You will find if your language has built-in support for a particular one, you know, or your machine has particular built-in support, you know, this is consistent with what you would see inside of C-type languages, Fortran-type languages, do it the other way. It's just, what is it? So, okay. And so that was kind of an image example. This is the same exact thing with getting a row of A. So then we say, here's an image piece, here's a row of A. You know. Anyway, I'm not going to sweat that too far. This one just adds in, because we're about to calculate our just-in-time A. And so this picture I kind of want to particularly just get you on. It's similar to what I was drawing over there. Right? You can imagine the line goes through. I want to label these, right, coming into their positions. So when I'm doing that, just think of the distances from the centers of those voxels to there. How would I calculate that?
You're saying the distance from the center of the box?
Yeah, or you could use that picture that I drew on the board there that has the centers marked with the distances. How would I calculate those distances?
We could do the same thing that we did in the back projection thing.
Exactly. It's the easiest, fastest way to do that, right? So what did we do?
Well, we first did our mesh grid, because that's just easy.
That gives us our X and Y locations for each center. Yeah.
And then you take Y times your sine, theta plus X times your cosine, and then you compare that to your offset.
To your offset, exactly. And if that is less than whatever your distance is at the absolute value, right, because you want to go either side, right? If that's less than it, then you're golden. Make sense? So yes, that is exactly what we want to do. So here we go. This is basically what a lot of that is. Now some of this I left in because, and I'll just explain what it is because it was just kind of trivial details. I do want you to try to remember this command. What does mesh grid look like? And how do you set up the numbers for that? Because that's a really helpful command in a lot of places. This is what I would call minutia that you can look up. But I will make a couple notes to you, right? How do we get the angle? Right? Well, our angle is going to be, if you consider what is my row number, and so you're going to get all the detectors in the first row, right? That's the first chunk, right? And then all the next rows worth, if you consider it in its original space, they get piled next to it. So if I divide by row, right? Or take, what is my current row number? That's what came out of the order. If I divide by sinodetectors, that tells me how far down that vector I got, which tells me basically in the original unreshaped square image, right? Where was I at? And that's actually going to give me proportional, right? Detectors and angles. It tells me how many angle jumps. So I floor that because I don't care if I was partway through it. Partway through the detectors is still the same angle. So remember, your row number is kind of like it's how many of these detector jumps. So the first angle, it's 0 through sinodetectors minus 1. The next angle is sinodetectors to 2 times sinodetectors minus 1, so on and so forth. So if I divide the row by sinodetectors and floor it, that tells me my angle number. Which angle am I at? Once I know what angle I'm at, right, then, you know, I'm going to want to figure out which detector was I on. That's the leftover chunks, right? So I know the angle number here. Now I want to know my detector number. Well, it came from the rows, right? So I take, what was my angle? That was this product, right? So this told me whatever angle I'm at. So angle times sinodetectors, that's the offset. Row minus angle times sinodetectors is that little difference. It's how far down that next piece you're at. Does that make sense? We actually do this one quite a bit, but it's easy to get confused. Most people are staring at me, which is generally kind of a dangerous spot. So, imagine this was my original setup, right? Of wherever, you know, I'm getting my sinogram on and that kind of stuff, right? On this is angle 0, angle 1, angle 2, angle 3, and then for angle 0, I have however many detectors you have, right, for each one. So this one is 0 up to number of detectors minus 1, right? And this is number of detectors up to 2 times number of detectors minus 1, right? 2 times number of detectors all the way up to 3 times the number of detectors minus 1. We agree? So on and so forth down the line. So if I wanted to get back to this number, if I divided by the number of detectors, 0 divided by number of detectors is still 0. Number of detectors minus 1, right? You know, divided by detectors, it's less than 1. And then when you do floor, it rounds to 0. So everything in here goes to 0. Everything here, right, when you divide by number of detectors, this is going to be 1. The very last item is going to be 2 minus 1 gives you 1. That make sense? Right? So, you know, if you divide by number of detectors and floor, whatever position you're in here, it gives you back this number. So it just tells you which angle position you're at. When I want the number of detectors, once I know this, right, like let's say I was here, right? So I would have calculated a 1. 1 times number of detectors removes that full row just before it. And so when I do what is my actual position minus the angle number times the number of detectors, just gives me this offset value. That's my detector number. That make sense? So that's all I'm doing, like right here, right? My current row, that's telling me how far down that dumb thing is. That's where my dot is, right? Minus angle times sinodetectors, that just removes how many steps down. So that has to be detector. Now, the detector we want, this is on absolute number, from 0 up to whatever. We now want to center it, so we subtract D2. Now it's going from minus D2 to D2, and we have an offset, right? Because remember, we were adding that little bit of wobble so it doesn't add up, and you get strongly enhanced circles. Right? That's the whole reason we put the offset in, right? Is we want to induce a little bit of wobble so noise cancels out, and we end up not getting these kind of strong ridges. If you pick your offset wrong, you'll get strong ridges. If you don't put an offset in, you'll get strong ridges. If you pick the right one, it'll tend to cancel the ridges out. That's the whole reason you do it. So you know you did that one not as good as it could be if you get too strong of a ridge, or if it fuzzes, or things like that. Good? Now, remember, this angle is not an angle yet. It's an index. So we have to take, we have that thing that was given to us, the angles. They tell us, you know, 0. The first one was at 0. The next one was 1, 2. Or it could have been 0 and 4 if you were doing 4 degrees at a time. Be 0, 4, 8, whatever. Right? So we take the angle number we had. This one is going to give me a number from 0 on up. MATLAB hates 0, so we have to do the stupid +1 thing because I can't count right. Right? I'm not bitter though. Right? So then we have to look up that angle number in here to get what is the number. Right? Now, technically speaking, the way MATLAB and all medical imaging things do it, they measure the angle from here and go around. This is 0 and it increases. How does anybody else in the universe do it? Here and there. That's why I have the minus sign. Because they put their stupid angle in the wrong direction. And they did it because on their imaging thing, it starts from here and they rotate around it. But they're technically going backwards. So annoying, and therefore, if you're wondering why do I have the minus there, it's to correct the fact they're going in the wrong direction. Right? If you don't do that, it should just flip your image. But
Yeah, for my back projection, it was upside down.
yeah, which you know, it's no biggie. Why the pi over 180?
We're going to use sine cosine, not sine degrees, cosine degrees.
Yeah, MATLAB does not correct it. This is the one time they've done it correctly, right? No person should use degrees. Radians is the correct measurement according to the universe, right? And I say that specifically because when you do calculus on it and you do calculations, radians falls out as the natural measuring system. You don't have to do any funny scaling things. If you pick any other measuring thing than radians, you have to put weird scale factors. So clearly the universe wants radians, so we should just get used to using stupid radians and stop dealing with old systems. Right? Nothing personal. Right? Okay, we're good on why I have to do that. So I just include these. These are very standard things. You should just get used to them, but I didn't think you would know them, so I gave them to you. AI we've done before. This is the only thing that would be new. This is the MATLAB command to turn a nice square matrix into a vector. Reshape, right? You give it the thing you want to, and you say rows and columns. And we want to make a single row that is the length of columns of A.
Yeah. A shorter syntax that I like to use is A1 equals A1, open parentheses, colon, close parentheses. It's the same thing. But.
Yeah. I just put it here because I like the explicitness that goes on. But yes, if you do the colon, it assumes automatically the end. In most versions.
Oh,
So that syntax started in the 80s, maybe even before. First time I coded in MATLAB was 85. So, it's old syntax. But on a few of the versions in between, they didn't implement that syntax. So what that means to me is that I'm never fully guaranteed either. So being paranoid, I also like the specifics of it. So that doesn't, I actually agree with you, it is shorter and cleaner that way. Just realize people, for some reason, like to change syntaxes on you. This one seems to have been pretty universal. But again, totally cool with it. Norm of AI, why put it here? Any idea? What's norm of AI going to tell you?
Is that the one that gives you the Euclidean magnitude of the whole thing?
Right? So this one is actually, this is going to be a variable. You're going to have to stick something in to calculate it. Right? I would, in this case, I want the Euclidean one. We're going to use this for two different things. One of them is, remember, we have to, in the projections, we have to take care of the scaling that multiplying by A does. Right? So this is needed for the normalizing and the projection. It also serves a second purpose. Anybody got an idea when norm of AI might go to 0? Exactly. Right? Is that possible? Remember, we have buffer pixels.
Oh, yes.
So it is actually possible. If it misses the image, that will become 0. And what do we do to scale things?
Type.
Yeah, which gives you a
Man.
division by 0. Yeah. So it'll either throw an error immediately or you get a nan and you never get your right number again. Right? So it's a good idea to just check and see whether or not this norm is 0. You'll see this, see that question, apply projection if there is information. It only has information if it hit the object. So that's what you're actually checking for. This norm AI is also going to be our check. Should I actually do this projection update? It'll be rare, but there'll be a few projection spots that will miss the object because you needed them for the boundary for guaranteeing that the object was contained inside, but therefore they missed. Therefore they have no information. Therefore, if you actually try to apply them, your whole image will go blank. Stupid, yes. So, but it happens, so project them. We're good? All right. So, as was mentioned before, right? Our detector position, that was our first one, that's kind of our B, our offset, minus the X position times cosine, right? And the Y position times sine, right? Because remember, that was just my X and Y matrix for their positioning, right? This is just mesh grid, 1 minus N2, right? This is a negative up to the positive, negative up to the positive, standard N over 2 stuff, right? So this is just X times cosine, Y times sine. That's just a line, right? and I'm subtracting that from the offset. That's my particular detector number. All right. So that is going to be how far away from this line is my detector. Okay? Absolute value gives you the absolute distance as opposed to plus or minus distance above or below line. This one just makes it absolute distance, right? And I check and see, is it less than distance? So if I had said, 1/√2, like 0.707, right? That's is it within 1/√2? Is the detector that distance from the line? Okay? And then I turn it back into a double because this is a Boolean.
Does that have to look the same?
No, it actually makes it a Boolean and it screws up your calculations.
Interesting.
At least on the last version I tried like 4 years ago, and I've just automatically cast them from now on,
Yeah, I haven't.
just out of paranoia. But early on, they were still floats. And somewhere right around 2000 and something, early 2000s, they used Boolean type ints for space savings. And I honestly haven't checked in the last several years, but I'm presuming usually they're not going to drop a data type. So it's just in like one word, it doesn't cost me anything for safety. All right, obviously we have to reshape it, and this is just norm. The default is that I do the square because I got it defined by it. That's not going to change my information content. I'm only caring if it's 0 when I'm doing the if statement. When I'm dividing, I want to divide by the squares, so I leave the square until later. It just saves me memory. Good? Awesome. Okay. Wow, that did not scan well. Sorry. So, tried to write projection things here just because all of you had said you had seen projections if I remember before. This was just so you have a memory of it, and then did not do the best job scanning it evidently. So anyway, you can just imagine there's my line, I'm doing the projection down, right? B minus AX, that's what we've been calculating, it's the residuals. Anybody take controls already? No, some. If you deal with controls, so it's one person. If you deal with controls, right, you're often doing the negative feedback error.
Yeah.
We call that residuals. That's actually what this is. You're technically actually doing the same type of an operation. Then depending on the scaling in your space, you're projecting into it. So it's automatically built in. So this is often a picture when you do modern control theory, this is how you write it. In classical, you write it as a differential equation. In modern, you do the matrix Laplace space of the differential equation.
Yeah.
Anyway, so this is just a reminder that, projection on to A is the projection onto A perp, right? Which is just I minus the projection onto A. All right, so they relate to each other by this. They're kind of like opposing spaces. And then this is just, if you're dealing with like a single vector, the easiest way to describe it is A, if A is the thing you're projecting onto, A times, this is a quantity, A transpose A. That's the norm squared. Inverse, sorry that it's, times A transpose. Right? So that's just the projection onto A. Right? So the projection onto A of B, you just have the B on the back. But A transpose times B is going to give you basically the length of A times the length of B times the cosine of the angle between them. So it's kind of a measure of how well do these line up. Okay. So if you think about this, this is kind of like a discrete space for the vector of them. Remember when we were doing like Fourier transforms and that, the inner product That's actually all a Fourier transform is, right? A Fourier transform is an inner product between a function and the complex exponentials, which are the basis function of Fourier space. So you're just doing an inner product. You're measuring what's the cosine of the angle between them, right? So it's an angle measurement that you're actually getting between the basis factors and the other ones. If you discretize those, you exactly get this. Right? So this, you know, the inner product in this sense is a discrete of those, and we're in essence doing this. This would be your basis functions that you're projecting onto. All right, so this would be projecting your function onto the basis functions of the eigens. That observation is what they call the fast Fourier transform. You just replace those with the complex exponentials, right? You know, in this kind of nice powers of 2 space, the way you go. Right? But that's really when you discretize the Fourier transform, that's actually what you're doing. Right? So just kind of a fun side thing. But from our perspective, that's a number and that's a number. So that's the only thing that's left. Right? Which is, so this is a scale factor, right? And this is the direction. So it just gives you your magnitude and direction. Right? And obviously it's in the direction of A, so you just find out how big in the direction of A. Good? Yay. So that's just a reminder. Oh, this one at least turned out better. Right? So this is with the offset put in. Right, so the only difference is now instead of having this line go through here, I projected it up. But you got this same lovely little normed area, right? That's still your residual difference. Your BI is just showing it's an offset orthogonal to the line, right? So we just have this B minus AI xi. So when we were just doing that, right, that's what we did on the previous page, right? Now we've got an offset value, what's called an affine space. That's all as opposed to a true linear space. Anyway, you know, that just gives you this offset. You know, that's the norm of the direction that we're in, so this gives me the scale of that difference between them and then in that direction. And if you think about it, this was a distance when it was all the way down, and I'm just taking part of that distance away from you by the offset. So it's pretty straightforward how that has to be. But this is going to give me my update to AXI. So that's why my next guess is the previous guess plus, that's just your weighting. This is just your projection, right? There over one of them in the direction of this, where you get the second one. That's all you're calculating. So that picture of the projection, direction of it, right? And the scale or magnitude. Put those two together, we're going to calculate that, multiply by lambda I, add it to our update new image. Okay? Okay. So feel comfortable with that, because now I want you to write it. All right, if, we just mentioned, you want to make sure you have information. So if there's not, what do I want to do, right? So calculate the residuals, otherwise the expression just gets up to the next line, right? You know, calculate your residual, that's your whole B thing, right? The B minus AX, right? And then your X next is going to be that update, right? Your previous X, then, you know, minus, you know, with the shift of lambda times your residuals in the direction of the new A. Okay?
Have we put the specific B scalar in a variable word yet?
Well, B was passed to us. That's the sine grade.
Right. But have we like picked out which pixel it's going to use yet?
Well, it's going to be the same as the row number of A,
Okay. So we did it.
which right, you've already calculated the row number, so that's. Right. So you've got the AI, you have the B because it was passed to you. So that's why I didn't call it sinogram, because just when you get into here, It's just a good reminder, oh yeah, that's B. All right. What do we do if there's no information?
Next is X last.
Yeah, don't do anything. Pass through the old image. You have no information, don't change anything. I'll give you a second code.
Would you mind going back to the previous picture?
I do not mind at all if I can. Previous. Just remember, you've put this in one number. So don't separately calculate these. I separated them because that's how math does it for the correct statement of the distances and that. When you think you've got them done, just wave at me. Just out of curiosity, which on this page, where is the residual?
That be your scale.
Minus that. It's this, right? Residual means it's basically what's left over. What's left over, this is what was measured. This is what you currently model should be the answer. AI is the direction of the path, that's the stuff that's all along it. So this product is what we think it should, what B should be. So this is our guess of B. This is what B really was with correct values of X. So that's how wrong did you get it? How bad was your guess of B? So we call that the residuals. So when you do residuals, that's what you want to calculate. And notice it's B, same row as A's. That's the I sub I. And again, that just saves you calculating because it's ugly when you write it all out. It just gets long.
I have a question.
Sure.
For X naught, are they gonna give us that as a row vector or a column vector?
Which would you rather have?
Well, I'd rather have a row vector, or.
Column vector.
Vertical vector.
Yeah, a column vector, because X should be vertical. So we just stick with it, that's what we want. Yes. Okay. Time-wise, we kind of have to anyway. Okay, here we go, boom. All right, so again, we just want to check that that norm is bigger than 0. In reality, we might actually want to pick that bigger to be some small epsilon, right? Just because we don't want it too close to machine precision, because divided by a really tiny number will still blow up in your face pretty bad. But that at least will stop the division by 0. So residual is pretty straightforward, right? B and its row position minus AI times whatever the X last is, right? So that's our residuals, and then X next will be the last X plus relaxation times residuals in the direction of AI, but AI was column vectors. Now you have to a row vector. You have to transpose it so you get a column vector to put it into your image space. So, right, and then divide by norm AI to remove any scalings. Right, which is just what we had on that previous slide. If you replace if you just put residual here, right, you have X next equals X last plus relaxation times residual in the direction of AI transpose, because we've got to get it to divided by the norm of AI. So it's literally just take the equation and go. And again, just like you had stipulated, if there was no information, then just copy the other one over. Okay. What should I do for cleanup? So this one is my X, and it's after I've run through all the iterations. So this is after the end of the for loop, right? So this is the X I'm going to pass back. How should I clean up my image?
So we gotta reshape it back and then scale it.
Okay, so that makes it nice, right? And we'd like to use that kind of matte to gray potentially if you wanted to. What should I do here? This is the else from our check. Did they send us good data?
Just some of the negative stuff.
You know, I could send them back. I could send them back X0, send them nothing back. I could send them some type of a thing to let them debug their code, so they don't think that my code didn't work at all. So I could pass them back, the condition that failed on here, right? So I could have, this could be condition number 1 or something like that that I stipulated up there. I could pass back columns of A, because they should know the size of the thing they sent. If I send you back one number only and I send you columns of A, then you could check and see, they think the image should be this big, I sent them this. So it gives you some debugging code. There's a couple different things you could do. So matte to gray, reshape it to an n by n, it's pretty straightforward. And I'm sending back the columns of A because it's debuggable information. Right? You get a 1 pixel thing coming back to you, it says you done screwed something up. Okay, we're good? All right, so this is now complete code, yay. So I figured that gets through to the end. So this is just a question to you, how would you call it? Right, you're gonna have to preset some stuff. What should I make as an initial guess?
Bunch of zeros.
Yeah, so zeros is a legitimate option. I could send zeros to it, right? I could send some initial guess, right? Filter back projection is amazingly fast, so sometimes people do the filter back projection and then pass it in and use this one to improve it. So they say, hey, let me get a good start guess, and I'll just take this and just try to clean it up, because this one allows me to clean things up. There's a lot of things you could do. So that's one reasonable initial guess. How can I pick the orderings?
Probably gonna want to get various angles next to each other.
Yeah, so we wanted to walk through, we don't want to miss anything. We want to walk through them with enough jump that it's more than just the detector range, but it should walk through everybody before it comes back around again. This is starting to sound complex, right? Turns out there's some beautiful math on this, right? If you divide by a prime number that is not in whatever number you've got for total number of the, detectors times angles. Right? So you don't want to divide by like 5, because you probably have 180 degrees, so your number is going to be divisible by 5. Right? But as long as you pick a prime number that's not in the base, right, it will go through every single one before it returns back. This is called a mutually coprime number. So as long as I pick a mutually coprime number, I'm good, i.e. in the number of histories you take, my prime number is not a factor. So it will meet that requirement. And then if I pick it such that it's somewhere around 30% of the way through, you'll be roughly 30% of the way through the angles, which would be about 60 degrees. If I went about 30 degrees, I should be about 1/6 of the way through the angles. So if I take my total number, let's say I had 20,000, then I could pick a prime number somewhere near, let's say I want around 30 degrees, I could do 20,000 divided by 6, and then just look up on the internet what's a prime number that's near 20,000 divided by 6. And if I just divide successively by that prime, add that prime number, and then divide by total number of angles times detectors, it will actually walk you through every history. Right? So it'll meet that requirement. This is a cool area from number theory in mathematics. I've always said if you can take more math classes, take more math classes. They're just stupidly useful and not where mathematicians think they are. Never ask them for where to apply it, but definitely ask them for the theories. Just reality. So those would be my guess. Try doing what you think is the best. I don't want to show you the answer. I'll show you. I gave you some pictures. This was what my code ramming did. You can see it starts out, the very first one, I start from 0. The upper left corner is the very first one. These are one iteration apart. So you can see it starts out, it's pretty fuzzy with a lot of streaks. After 0, it gets smaller and smaller. So eventually it gets pretty darn good by the end. Right? So for the number choices that I did, that's what it does. All right, so you can see it in. Try different numbers, try making your own startup areas, and we'll compare what we get, and I'll show you how I launch mine, the particular number choices I did. And we'll do that at the beginning, and then we'll go into BIP. Good? Awesome. Have fun. Oops, there's my code, but I don't want to leave that up for long.